Okay, hi everybody, welcome back to another tutorial. This time we will try to understand the relation between the shear force and the moment functions and diagrams. Okay, and basically we want to answer the question why they have such shapes. I believe it's time for us to try to understand or look at the problems in another way after doing a couple of problems. That's it. So let's get started. Okay, so we will cover the following. First, we're going to do some review about the slope of a line, differentiation, integration. Then we're going to look at the relation between the shear force and the moment functions, just by looking at the functions. And then we're going to take a look at the shear force and the moment diagrams and how can we relate these two. Then we're going to do the first example with an easy to find moment from V. Then we're going to do a problem or example 2 that's not as easy as problem or example number 1. So let's get started. So what's the slope of a line? The slope of a line in the plane is defined as the change in y coordinates divided by the corresponding change in x. Okay, so it's delta y over delta x. And the y's and the x's are between two distinct points on that line I'm interested in finding the slope for. We can basically say the slope m delta y over delta x equals rise over run. This line has a positive slope and this line has a negative slope. This line has a zero slope and this line has undefined slope. So that's a review for all of us actually, guys. So we know the meaning of a positive, a negative, a zero, and undefined slope. I'm really interested in the zero slope, and that's going to be clear after we do the example. So what about the slope magnitude? If you increase the magnitude, forget about the sign of the slope. Just increase the number of the or the magnitude of the slope. The steepness of the line increases. That is, it becomes closer to the y-axis. So if we have this x and y-axis, this red line has a slope. Let's say it has a slope of, for example, 1. The green line will have a slope of maybe 4. Okay, because it's closer to the y-axis. And if the purple line has a slope of -1, the blue line will have a -4. Okay, just looking at the magnitudes without the sign. Okay, now let's look at the differentiation. For a real valued function of a single real variable, the derivative at a point equals the slope of the tangent line to the graph of the function at that point. So let's say the blue line represents the function and the brown or brownish line is the tangent line to the function described by the blue curve. So the slope of this straight line can be found using the derivative of the blue line at the point of where it touches the curve. And we know most derivative computations eventually requiring taking derivative of common functions. So we will look at one of the common functions, which is the power functions, or basically we're going to look at the derivatives of powers. So if I have a function that's f of x equals x to the power n, where n is any real number, then if you take the first derivative, you'll get n times x to the n minus 1. The second derivative will be n minus 1 times nx to the n minus 2. And the third derivative is n minus 2 times n minus 1 times nx to the n minus 3. So if you start with a function of power n, and after taking k derivatives, the power of the resulting function is to the power of the function. The resulting function has a power of n minus k. For example, if I have f of x, which is x to the fourth, so n in this case equals 4, the third derivative will be f of x equals 24x, and we notice that the x is to the power 1. So to the power 4, after 3 derivatives, that's 4, or that's n minus k, 4 minus 3, that's 1. So the resulting function should have a power of 1. On the other hand, integration is defined informally to be the area of the region in the xy plane bounded by the graph f, the x-axis, and the vertical lines x equals a and x equals b as shown in the graph. Okay, such that the areas above the axis add to the total and the areas below subtract from the total. This is a very major concept in all engineering branches, but in our case we're going to take this concept in trying to find the moment after we get the shear by integration or by calculating the area under the curve. So for example, okay, before we go into an example, integration is the opposite operation of differentiation. So integrals of powers, again, so if you have a function that's f of x equals x to the n, where n is any real number, then the integral of f of x equals x to the n plus 1 over 1 plus n. If we integrate again, we're gonna get x to the 2 plus n over 2 plus 3n plus n squared. And if we triple integrate or integrate for the third time, we're gonna get this expression. We notice that the first one, we increase the power of the original function by 1, and in the second one we increase the power by 2, and in the third one we increase by 3. So if you have, let's say, a function that's x to the 2 or x squared, after taking the first after integrating the function once, you'll have x cubed. Integrated again, you'll have x to the 4th. Integrated again, you'll have x to the 5th. And opposite to this was the differentiation. If you start with the x to the 5 and you take the first derivative, it's going to be x to the 4, or the function will have x to the 4th term in it. And if you take another derivative, the new function will have x to the 3rd power in it. Okay? Now, let's try to look at the relation among W, V, M, and delta diagrams in general. Now, remember, if we have the 4th order linear equation, differential equation, that's EID to the 4th derivative with respect to x equals negative WX, and we've done a couple of tutorials on how to use this equation to get the elastic curve equation. I'm going to use the same concept here for this uniformly distributed load and look at the following. The load is a constant, is a number, so it has a 0 slope. Okay, no slope or 0 slope, so it's a constant number. Wx in this case will equal probably 2 kibs per foot or 10 kilonewtons per meter. Okay, now if I integrate this once, I will get the shear equation, and we notice it started with a constant. The shear equation, it has an x term to the power of 1. If I integrate it again, I will get the moment equation, and we see the moment equation will have x to the 2nd power. Let's integrate it again, we will get the rotation equation, and now we have x to the 3rd power. And if we integrate it one more time, we'll get the deflection or the elastic curve equation. That's the delta x, and we see that x here is to the 4th power. Now, to double check your answer, try to differentiate. So you start with the very bottom equation, that's delta x, and start to differentiate this equation not once, not twice, not 3 times, probably 4 times, to all the way to get to the wx. When you differentiate it once, basically you go from the delta now to the phi equation, to the theta equation. So you start with the x to the 4 and you get x to the 3 terms, or x to the 3 term, and now you differentiate it one more time and you get x to the second, or x to the 2 power. Then you differentiate one more time and you get x to the first power. Then if you differentiate it last time, you will get a constant. So that's the thing we want to understand, that if you start with a uniformly distributed load, the shear equation should be a straight line, since x has a power of 1 in the shear equation, and the moment equation will be parabolic, okay, and so on. And if we start, we will see in a couple of the examples I'll provide, that if we start with the wx that is linear, basically what I'm saying here, that it's not a constant, it's not a uniform distributed load, maybe it's a triangular load. We will see that if we start with a triangular load, that means we have an x to the first power in the load equation. Then we will have x to the second power in the shear equation and x to the third power in the moment equation. This is the example we looked at. Okay, we can see that the shear equation has a x term in it, so it has a straight line, and by the way, it has a negative slope. Now, the moment shape looks like that, and the moment equation has x to the second power, that's why it looks parabolic. And if we look at the theta equation, we will see it has the x cubed term, and the delta will have the x to the 4 term. Now, what about a cantilever with a uniform load? So again, they start with a load which is a constant. Now we will have a negative x, so negative slope. Then we will have the moment equation with x squared, and we will have the rotation equation with x cubed, and we will have the deflection equation with x to the 4. One of the purposes I'm doing this tutorial is to try to show you how can we determine the shape of the moment, the shear or the moment, the rotation or the deflection curves, if we know the values of the points. For example, is the moment diagram concaved up or down? Is the rotation diagram concaved up or down? We'll discuss this later on in this tutorial. Now let's look at a simply supported beam with a triangular load. Now we start with a load that's not a constant, it's linear. So we start with x in the load, or x to the first power in the load equation. Okay, so we can see this equation representing the triangular load, unlike the uniformly distributed load case, has non-zero slope. Okay, so we see that the shear equation has x to the second power in it, and the graph probably is not a very nice representation, but it should look like a parabolic shape. And for the moment, it's to the third power, the rotation is to the fourth power, and the deflection is to the fifth power. Now let's do the parabolic case. What if you have a beam that looks like this? It has a loading pattern that looks like this. Okay, so we start with this equation, which is to the second power. Now the shear is to the third power, the moment is to the fourth power, the rotation is to the fifth power, and now we see the deflection is to the sixth power. Let's see example 1 very quickly, very easy example. You have a beam with a Wx constant, zero slope. That means it's an uniformly distributed load on a simply supported beam. Okay, if I integrate this, I will have, or if I integrate the load equation, I will get the shear equation, which is a linear equation. And if I plot it from 0 to L, I will get this straight line. Now, how can I get the moment equation? What I do, I integrate the shear equation, and I get the moment equation. And if I do this, I will get x squared in this equation. And it will look like this. Now, if I stop here and if I ask you in an exam, would you do the integration? If and only if the shape of the shear diagram is simple enough that you can calculate the area beneath it, do the calculation or find the moment by calculating the area under the shear diagram. How's that? For example, we look at this red triangle. The area of this red triangle is basically the value of the moment here. Okay. Now, if you want to calculate the rotation, you integrate the moment equation and you'll get this equation. Now, if you want to calculate the deflection, you integrate the rotation equation and you'll get the deflection. This is a very easy example to do, but the example I'm interested in is this example. Now I have a triangular load, increasing triangular load from left to right, and I have a point load or a concentrated load on a beam AB. The question is, draw the shear force and bending moment diagram for the beam shown in this figure. Locate the maximum moment location and value. Okay, so our goal is to find the shear force diagram, the moment diagram, plus we need to find the location and the magnitude of the maximum moment. Okay, the solution. We start by finding the reactions. To find the reactions, any distributed load has to be concentrated on the beam. And since we already have the 20 kilonewtons, I'm sorry, this should be 20 kilonewton, not 20 kilonewtons per meter. Since we have the 20 kilonewton concentrated already, we need to concentrate the triangular load. The way to concentrate the triangular load is to find the area of the triangle. The area of the triangle is 6 multiplied by 10 multiplied by a half, and that will give me 30. And the location of the concentration is going to be 1/3 from the 10 kilonewtons per meter, or 2/3 from the supports A. Now all I need to do is to sum the moments, sum the forces in the y direction. I have AY plus BY should equal 50, then the 50 is the 30 plus 20. Now I need to take the moments about A and set that equals to 0. If I take the moments about A, and now I'm assuming that the counterclockwise is the positive rotation or positive moment, what I will have is 12 times BY, 12 is the whole length of the beam times BY, minus 20 times 9 minus 30 times 4 should equal to 0, and if I solve for BY, I will have 25 kilonewton, and if I substitute back into the summation of the forces in the y equation, I can solve for the AY to be 25 kilonewtons. Now let's do the shear diagram. This is the beam. So the shear, or V at A, or x equals to 0, is basically the reaction at A, which is 25 kilonewtons. And I will denote the location of this 25 kilonewtons by a dot. I will not connect the dots that I will get along the beam until we explain one more thing. Now, the shear at x equals 6, we can do this a couple of ways. The first one would be if I integrate the load equation between 0 and 6. And the load equation is basically the load of the inclined line. And remember, the integration of this line is basically calculating the area beneath this line. This is what I was talking about, and we will do it two ways. If I want to calculate the value of this integral, I can calculate the area of the triangle, which happens to be 30. And we add a minus sign to it because it's under the integration. We can see this minus sign. And we have to add the V0, the shear we started with. We started with a shear of 25 kilonewtons. That's the shear at the previous point. And then we add to it the minus 30. So it's 25 minus 30. I will end up having Vx, or V at x equals 6 equals negative 5. Remember this value, negative 5. Or we can do it the long way. We can get the equation for the line, which happens to be 5 over 3x, and the negative sign is the negative outside the equation of the line or the load. And if I do this, I will have 25 minus 5 over 6 x squared, and if I substitute x to be 6, I will have 25 minus 5 over 6 times 6 squared. That will give me negative 5. So in both cases, calculating the area under the triangle or doing the integration will get me to negative 5. So this is the negative 5 location. Then what we can do, we can go ahead and ask ourselves, what happens between this negative 5 kilonewtons and the concentrated load? Is there any load in here? No, there is no load between the end of the distributed load and the beginning of the concentrated load, so I should not have a change in value in the shear. And under the 20 kilonewtons will try to put me down or drag me down, or pushes me, or this force will push me down by 20 kilonewtons, and I'm already at negative 5, and I'm gonna be pushed 20 units. I'm gonna go to negative 25. Then after the concentrated load to the reaction, we don't have anything, so we will basically move this point, so the value at B equals negative 25. And remember, the reaction at B was positive 25. If I add it to this 25, I will end up having a 0, and that will close my shear diagram. Notice that I didn't draw any lines between these points. I'm waiting for the following. How to remember concavity? Remember, if we have a shear diagram and you want to draw the moment diagram, you got the beginning and the end of this moment diagram, but you don't know, is it concave up, is it concave down? So let's take a look at an easy way of remembering these tricks. Okay, from the load, you can apply the trick I'm gonna show you here on the load, so you can know the concavity of the shear diagram. You can apply it on the shear diagram to know the concavity of the moment. You can apply it on the moment to know the rotation, and of course you can apply it on the rotation to know the concavity of the deflection. Okay, now we will use just the load as an example. Okay, and again, same applies to V, M, and theta. Case 1. If the load is positive and decreasing, okay, what does that mean? This load is positive because it's pointing out, upward, and it's decreasing in value. Okay? Concavity of the shear will be this one. Case 2. Load is negative and decreasing. This is negative because it's pointing downwards and decreasing in value. The concavity is this way. Case 3. Load is positive and increasing. it's positive, pointing upwards, and increasing in values. The concavity is this way. The last case is the load is negative and increasing, which is this load, and this is our case, and the concavity would be like that. Okay, how can you remember all of this? Here's the trick. Load is positive and decreasing, so this is the black curve represents concavity. The plus represents the increasing, the positive load, and the red arrow represents the decreasing in value. Okay, negative and increasing, positive and increasing, negative and decreasing. So finally, if you remember how to draw this in an exam on a scratch paper while you're doing the homework and know the meaning of these symbols, you can remember the concavity. Now let's go back to shear diagram. This is the beam, and we had these points. Okay, now we want to apply whatever we know here to the shear diagram. So what type of a load do I have? I have a negative load because it's pointing downwards and increasing. So I am talking about this section. So the concavity is like that. This is the first thing, it's going straight up, and this is the concavity. After that, I don't need to look at the shape or the oval shape I have. Between -5 to the next point is straight line, then I'm gonna go down 20, then I'm gonna go straight horizontal line, then I'm gonna go up 25 to close the shear diagram. What about the moment diagram? This is my beam, this is my shear diagram, and here I'm gonna try to draw the moment diagram. Okay, what is the moment at x equals 0 or at A? This is a hinge, so the moment should equal to 0. Okay, so we have a 0 point at A. What about the moment at x equals 6? Okay, now here's the thing. You can find the moment at x equals 6 if you know how to calculate the area under the curve of the shear diagram between 0 and 6. The problem is this area does not have a formula. It's not a square, it's not a rectangle, it's not a triangle. It's a function. So we cannot use the simple trick of calculating the area, but we know that the area of under a graph is basically integrating the function, if I know the function of that graph. So what I will do, I will start with the moment m0, which is 0, and I will add to it the area or the integration of the Vx dx, the area under the shear diagram between 0 and 6. And I start with a 0, m0 is equals to 0 because m at A is 0, and I will integrate this equation we got from previous steps, and this is the moment equation now. And if I substitute m equals 6 into this equation, I will get 90. This is the 90. Now, again, if I continue doing this, the 75, basically what we need to do, if we know up to the point at 6 meters that it's 90 kilonewtons meter, to find the 75, what we need is to add this area to the 90, which is 3 by 5, and 3 by -5, that's -15, and we add it to the 90 and we get 75. And to make sure that we've done it correctly, the 75 is exactly the area shown here as well as the area shown here. So what about this new area? The new area is 3 by 25 for the reaction at B, and we will get 75. Now we have an M max before the 90. Why? Because the shear diagram crosses the horizontal just before 6 meters. The question is, what kind of shape do we have for the moment diagram? Is it a straight line? Is it concaved up? Is it concave down? If I want to apply the same logic I used before this, I will look at the shear diagram and see, is it positive or negative first? For the load diagrams, the arrows indicated the direction of the load, so we know if it's pointing downwards it's negative, and if it's pointing, if the arrows are pointing upwards, are positive. But for the shear diagram, if the shear diagram is located above the x-axis, we consider it as positive, and if it's located below the x-axis, we consider it as negative. Is our shear diagram above the x-axis? Yes, so it's positive. Is it decreasing or increasing? As we go from left to right, we find it's decreasing, so we are talking about this case. This is the shape or concavity. Then, looking at the shear diagram, if the shear diagram has the segment of the shear diagram I'm talking about has a zero slope, if I integrate it, it will have x to the first power line, so it has an inclined line with a slope, which is this line, and again for the other segment it should have another slope. Let's keep going. We need to find the maximum moment value and location. We know the locations it's somewhere before 6 meters, but maximum moment can be found at the zero shear location. Okay, that's how we identified in the first place the maximum moment. We set the shear equation to 0 and solve for x. That's it. So Vx equals 25 minus 5 over 6x squared, and set it equals to 0. So solving for x, we will find x to be 5.47, which is below or just before 6 meters. Now, what about the value of this moment? We take this x and substitute it into the moment equation. The moment equation, we have it like that, and if we substitute 5.47, we will have 91.29 kilonewtons meters. So the final shear diagram looks like this, and the final moment diagram will look like this. That's it for today, and thank you for watching.